All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna be doing, how do I say this? Well, I mean, we're doing a study stream, more of a research stream, but yeah, pretty much a study stream. We are still learning about feed-forward neural networks, but this time it's not about training and testing neural networks. I want to get a better understanding of I'm not sure how to explain this. I want to get a better understanding of what exactly neural networks do with the input, because I know that a feed-forward neural network consists of an input layer, an output layer, and in between the input and output, there's going to be a number of hidden layers, and each layer, including the input and output layers, they consist of a certain number of neurons. So data is processed throughout the neural networks through each of these layers. The data passes from one layer to another to another to another, and it's transformed in various ways. Now, what exactly is happening during that transformation is what I want to learn. I want to learn. I guess the best way to I guess the best question that I can ask there is, yeah, what exactly do neural networks see, or feed forward neural networks? What exactly do feed forward neural networks see in the input, and what features are the neural networks extracting, or, well, let's say one neural network. In this case, what features is the feed forward neural network extracting from the input, and how is it transforming it through each of the layers? Well, not how. I know how, that's through, a linear transformation, but what is it transforming those features into? What exactly is it doing with that data? That's what I'm trying to understand, because we've learned how to build and train and test feed forward neural networks, and that's great. At this point, I can build, train, and test a feed-forward neural network to classify images, and I'm not limited to just the, what do you call it, fashion MNIST dataset, because I did try. So okay, in our example, we were taught using. Give me a second. Right, in our example, we were taught how to train a classification neural network, or would this qualify as a classifier? Like, would we be calling this a classifier? I guess so. It's not inaccurate to call it a classifier. Give me a second. Let me just refresh my stream manager page and make sure the stream is live, because I just noticed that the feed was frozen on that end. Man, I've been trying to stream, but it's been a couple of days. It's been a couple of days. These past couple of days have been something. Just, that's all I can say about it. So because of that, I just wasn't able to stream. Anyways, I checked the stream manager and we are good. Now, what was I saying? Yeah. So, in our example, we were taught using the fashion MNIST dataset. We were taught how to build, train, and test a feed-forward neural network using the fashion MNIST dataset. That's a dataset of clothing-related images, and each image can be classified as one of 10 classes. And yeah, so you have the fashion MNIST dataset, but other than the fashion MNIST dataset, you also have you have a number of other datasets. One of them is the MNIST dataset itself. This is a dataset of handwritten digits, basically just numbers. But the important part there is the handwriting. These are handwritten digits. And what we are trying to do is train the neural network to be able to recognize the number. In this case, it's going to classify it as, you know, a number between 0 and 9. But yeah, that's the idea. We have to train this neural network so it can recognize the digit despite of whatever handwriting is used. And that was pretty straightforward to do as well. I pretty much didn't have to change anything in the neural network or in the training and testing code. The only thing I had to change was the data set that's being plugged in. So new data set, and actually no new data loader either. Literally just the data set. If I yeah, I think it's literally just the data set. So we had the train and test data sets. I just had to change which data set is being loaded, and that was that. Why was I telling you this? Yeah. So my point is that, okay, I'm able to build, test, and well, build, train, and test feed forward neural networks, but I'm not satisfied with my understanding of how feed forward neural networks actually work and what they are doing on a deeper level. Like I understand that numbers are being, or data is being transformed. I understand that there's a linear transformation taking place, and then there's the data is being passed through a nonlinear activation function, and then the step is kind of repeated again and again, depending on how many hidden layers the neural network has. I understand that that's what's happening. So I understand. How do I say this? I understand the math behind it, but conceptually, I don't understand what exactly the network is doing by processing these numbers, by processing this data that we are feeding into it. So what I did is I asked a language model. In this case, I think I'd asked DeepSeek, and I did get an answer, but that was on a different system. So what I'm going to do is I'm gonna ask the question again. And I think today's stream is going to be mostly about just reading, and trying to understand exactly, trying to trying to understand what the feed forward neural network understands from the input. That's a good way to put it. Okay, so let's create the prompt. Okay, I recently learned how to build, train, and test feed forward neural, yeah, feed forward neural networks in PyTorch. I used the fashion MNIST and MNIST data sets for this purpose. While I understand how to, again, build, train, and test FCNNs, I don't. Oh, by the way, I keep saying FCNN. I need to look into whether FCNN and feed forward neural network are the same thing, or if FCNNs are a slightly different concept. I need to look into that because so when I was reading up on what do you call it? I guess I was reading up on feed forward neural networks. Yeah, I think it was on feed forward neural networks. I was reading the sorry, I was having trouble remembering. Yeah, I was reading the Wikipedia page for it, and it went down to the perceptron section, and then it went down to the multi perceptron or multi-layer perceptron section, and there it mentioned something about multi-layer perceptron being used or being a misnomer for feed-forward neural networks, or it was something along those lines. Give me a second. Let me just let me just open up that page here. Okay, feed-forward neural network wiki. Okay, so we have the page here. Let's bring the page here, and let's also switch to dark mode. Great, awesome. I I love that feed forward Wikipedia. I love that Wikipedia has a dark mode now. Not now. It's been I want to say it's been a couple months, but I think it's been a year at this point. Maybe more. I don't remember. But yeah. Anyways, yeah. For those of you who don't know, Wikipedia does have it has like a theme setting, so you can click on these binoculars or these glasses, and then aside from other appearance related settings, you also have color, and here you can choose between light and dark. Okay, cool. So feed forward neural network. I was reading up on the wiki page because, dude, okay, the thing is, like I mentioned before, I understand. Okay, I guess it's hard for me to put into words what exactly it is that I understand. Like, well, no, it's hard for me to put into words on what level I understand. Like, should I call it the conceptual level, or, well, yeah, I understand on a high level. I guess, yeah. So I understand on a high level. Actually, no. Would it be on a high level or on a low level in this case? Because I understand the math behind it, but I don't understand what the calculations are actually capturing, or what the algorithms are actually capturing. Anyways, so I understand, like I mentioned before, I understand how to build, train, and test feed forward neural networks, but I don't quite yet understand. Um, I don't quite yet understand what exactly they are doing with the data. Um, so okay, yeah, here's the thing that I was mentioning before. Multi-layer perceptron. A multi-layer perceptron is a misnomer for a modern feed-forward artificial neural network consisting of fully connected neurons, hence the synonym sometimes used of fully connected network. Often with a nonlinear kind of activation function, organized in at least three layers, notable for being able to distinguish data that is not linearly separable. You know what? I feel like there's something for me to explore here, but I think I'll explore this off stream. For now, let's continue with this. Okay, cool. Um, Man, I completely forgot that I was writing this question. Okay, so while I understand how to build, train, and test feed-forward neural networks or fully connected neural networks, I don't quite um, understand. Give me a second. Okay. I don't quite understand what exactly they are doing with the data. I don't understand how the number of hidden layers and the number of neurons per layer impacts impacts the result, or impacts the changes things. Let's just say changes things. Changes things. I don't understand. Sorry, zoned out. Okay, give me a second. Just a minute. Okay, all right. Where was I? Right. So I don't understand how the number of hidden layers and the number of neurons per layer changes things. I don't understand. Give me a second. Right. Uh, what was I? Sorry, I'm doing something else on the side. Okay, yeah. I don't understand how the number of hidden layers and the number of neurons per layer changes things. I don't understand what kind of information or pattern each layer is capturing from the data. I think you understand. I think you get the gist of what exactly I don't understand. Okay, so, okay, are we done here? Okay, cool. Oh, You know what? I'm noticing something else here. Okay. But understanding these principles. Okay, so it mentioned dropout in L2 here, which I haven't yet done this with. Okay. I wonder if I should also mention. Oh, you know what? Yeah, I wonder if I should also mention um, what exactly I've learned to use. Um, just for your information, so far I know, so far the FCNNs I have built have only used linear and ReLU uh, layers with a softmax used at the end for to calculate probabilities. Okay, so let's start reading. Okay, so the user has been working with feed-forward neural networks in PyTorch using datasets like MNIST and FashionMNIST. They know how to build, train, and test these models, but are struggling to understand what's happening under the hood. Exactly. Okay. Specifically, they're confused about the role of hidden layers and neurons. Uh, no, wait. The role of hidden layers and neurons and what each layer is actually learning from the data. Okay. Yep. Yep. They mentioned using linear, ReLU, and softmax layers. So I need to explain how these components contribute to the network's function. First, I should start by breaking down what an FCNN does step by step. Maybe start with the input layer. In MNIST, each image is 28 by 28, so flattened into 784 features. I didn't think about it in that way. Actually, okay, so this is a good point too. This is a good place to like kind of reflect. Um, I was so okay. I knew that it transforms, or well, all 784 pixels get fed as input into the neural network, and what I knew is that the neural network's next layer, or well, first hidden layer, it starts to capture or extract, quote unquote, extract features from this data. I didn't know that these 784 pixels were themselves also features, or maybe I just wasn't using the right terminology and that's why I didn't realize it. Okay, each neuron in the first hidden layer connects to all 784 inputs. The weights and biases here might be learning basic features like edges or simple shapes. Then each subsequent hidden layer builds. You know what? Okay, I should write this down. As the questions come up in my mind, I should write this down. Okay, so um, try to visualize. Try to visualize what each. How do I say this? Try to visualize what each hidden layer in the feed forward neural network is learning or extracting from the input of or from the input in the previous layer. Okay, right. Where was I here? Okay, then each subsequent hidden layer builds on the previous one. More layers could mean more complex feature detection. Okay, that's another thing, right? Visualize. We can remove this try to. Visualize feature detection. Visualize visualize the feature detection done by each layer in the FCNN. Okay, but how does the number of neurons per layer affect this? More neurons might allow the layer to capture more features or variations, but there's a balance to avoid overfitting. Okay. ReLU activation introduces nonlinearity, allowing the network to model complex patterns. Yeah, this was actually something that I thought about a long time back that I wanted to do research on this thing. Um, Understand exactly how non-linearity helps the network. Okay, where was I? Yeah, ReLU activation introduces nonlinearity, allowing the network to model complex patterns. Without it, even multiple layers could just be a linear transformation. Softmax at the end converts outputs to probabilities. Okay, I should explain how the network transforms data through each layer. Maybe use an analogy like feature hierarchies. Lower layers detect edges, mid layers detect shapes, and higher layers combine them into recognizable patterns. See, this is interesting to learn. It's interesting learning that each of these layers actually does this, because initially when we built this neural network, none of this stuff was mentioned, right? It wasn't mentioned that, okay, this layer is going to be doing this thing, and then the layer after that is going to be doing this thing, and then the layer after that is going to be doing this thing. None of that was mentioned. So, like, from my point of view, it was just like, okay, let's try adding more layers in there and see if it helps. It definitely didn't help the training, because with a higher number of layers, um, the how do I say this? With a higher number of layers, more training was required, because it would start out at a horrible accuracy compared to if there were only 3 layers. I tried increasing it to like 10 layers, And I didn't understand at the time that I think maybe um, what's happening is because the network is becoming more complex. So maybe it's able to extract even more complex data with each iteration, with each, well, not iteration, with each new layer. It's able to extract more and more features, but that also means that it's going to take more time to train. Though I feel like once we get past that training thing, we're gonna have a fairly accurate shit. I missed the ad timer. Okay, there'll be an ad starting in like 15 seconds or something. Okay, I feel like once we do manage to train this network, we're gonna have a fairly accurate network because solely because the network is able to capture so much important information from the input that it can more accurately classify, you know, the whatever the image is. I don't know if I explained that very well, but like I feel like with more layers, it's going to be able to learn more complex patterns from the data. But my problem is that I'm trying to understand exactly what it's learning, what complex patterns, what quote unquote complex patterns it's learning from the data. That's what I'm trying to understand. But I do understand that once it does learn this, okay, there's an ad playing right now, so I'll take a hydration break and I'll see you guys in 30 seconds. Okay, welcome back. So I was saying something about the network capturing complex patterns and the fact that I am trying to understand exactly what the network is capturing with each layer, actually, not just the entire network, but what exactly each layer is capturing. And if I'm able to visualize that at some point, that would be great. That would be super helpful if I manage to visualize that at some point. But again, in order to visualize it, I need to understand exactly what the network is learning, what the network is seeing, and what the network seems to be processing. I need to find a way to step through the data each time in the neural network. I don't know if what I just said made sense. I need to find a way to like report back data each time the neural network runs. So I need to look into ways to do stuff using. So currently we are using nn.sequential, which is sort of a container in which you put a bunch of functions and then it kind of executes all those functions in that order. So I need to see if I'm able to put something within nn.sequential, or if I'm just going to have to break it up into, you know, multiple parts, which is, it's not really a big deal, but it's just that it's just going to be more code. That's it. It's not really that big of a deal. But at least in this way, I'm going to be able to at least in this way, I'm going to be able to report back information and figure out exactly, you know, what the network is seeing. And maybe if I'm able to visualize what the network is seeing, I might be able to see some pattern in it. That just occurred to me that, yeah. So okay, in this case, it's an image, right? The image can be visualized. So what if the data is also visual, though the data gets flattened before we put it into before we pass it into the network. So I'm gonna have to rebuild the data. Yeah, yeah. I'm gonna have to rebuild the data somehow. Or well, not rebuild the data. I'm gonna have to like find a way to put the data back into, how do I even say this? So like the image is a 28 by 28 image, right? And that gives us 700 and whatever, 700, what was it, 38, 68, 84. That gives us 784. If we look at the neural network's definition, that leads into a hidden layer with 512 neurons. Where is it? Yeah. So this is our input, right? And this goes into 512 neurons. Wait, did I say that? Did I say that right? Yeah, yeah. So this defines that's the number of out features, right? So that's um yeah, the number of out features is the actual number of neurons in the hidden layer. Okay, so this becomes our first hidden layer, right? And then we have our second hidden layer here, which takes in 512 and then also gives out 512. So our second hidden layer is it also has 512 neurons. Now the thing is, the input is 784, which then becomes 512. So now the thing has kind of like shrunk down, right? So I need to figure out a good way to visualize this. I need to, well, okay, not just visualize. I need to figure out a good way to turn this into a something by something image, because it can't be a 28 by 28 image anymore, right? I have to find a way to, or well, I have to figure out the calculation for scaling this down. And well, no, this is scaled down. I have to figure out the calculation for fitting this scaled down image into, actually, okay, a 512 image. What is 512 divided by 2? 256? No. Is it? Well, okay, 256 multiplied by 2 is 512. So if I wanted to make if I had 512 in total, I don't think it can be a 256 by 256. That's not going to work. No, that's actually bigger. Yeah, that's definitely not going to work. Oh, I could try doing this instead. Let's calculate down here. Let's calculate 512 divided by, not divided by, 512 to the power of 2. This should give, oh, that's not what I was looking for. Square root? Oh, square root. That's what I'm looking for. Yeah. Does that work? That doesn't work. Okay, from math import square root. Square root? Yeah. So it would be a 22 by 6 something. Okay. So something we could do is, now I need to find a way to um make this like a whole number, because I'm not sure what I'm going to do with the decimal. Because like if we do 23 multiply, no, 23 to the power 2, that gives us 529. Yeah, I need to find a way to. Oh, is there? I wonder if there's any. So okay, PyTorch or Torch Vision does have some transformation methods. I wonder if there are any methods that help us transform data. Was it here that I'd seen? Give me a second. Let me. Okay. PyTorch Vision transformation methods. Transforming and augmenting images. So they have a couple of, yeah, okay, so this is it. Let's open this up. Give it a second to load. Okay, Torch Vision supports common computer vision transformations in the Torch Vision.transforms and Torch Vision.transforms.v2 modules. Transforms can be used to transform or augment data for training or inference of different tasks, image classification, detection, segmentation, video classification. Okay. You know what? Hold on. I have, no, okay. I'm doing stuff with PyTorch. Let's give it some context. I have a 28 by 28 image. I flatten this image and pass all, um, actually, yeah, okay. And pass all the 784 features into a linear layer with 784 in features and 512 out features. The image has already been flattened. So at this point, uh, I don't know how to visualize the 512 features. I want to turn those 512 features into an image that can be actually, yeah, into a something x something image that can be visualized. I'm wondering if there are any libraries that can help with stuff like this, and do you have any recommendations for what I should do? Okay. Um, right. Visualizing linear layer features as images in PyTorch. After flattening your 28 by 28 image into a 784 element vector and passing it through a linear fully connected layer, 784 in, 512 out. I like that it understood all of this. You now have a 512 dimension feature vector. Do I? No, it's one flat array, isn't it? Okay, visualizing such high dimensional data can be challenging. Hold on. Do I really? Wait a second. Let's let's do something here. Um, okay, so first things first, we run that, and then we do something here. Let's do a equals tensor 1, 2, and then LO1 equals, okay, we can make this TO1. LO1 equals NN dot linear, takes in 2, gives out 4, and then RO1 equals LO1, which takes in TO1, and then we want to print out the shape of RO1. Yeah, it's one dimensional. Why is it saying 512 dimensional? Okay, 512 dimensional feature vector. Visualizing such high dimensional data can be challenging, but there are several established practices and libraries you can use. Uh, direct image reshaping. Since 512 is not a perfect square, you cannot directly reshape it into a square image. However, you can reshape it into a matrix that's as close as possible. uh, that's as close to square as possible. This is a naive visualization and doesn't preserve any spatial locality from the original image, but it can sometimes provide rough insight into patterns encoded by the features. Okay. Dimensionality reduction techniques. For more meaningful visualization, apply dimensionality reduction techniques such as principal component analysis. That is something that I'd been meaning to look into ages ago with just regular data science stuff. So I love that it's coming in now. Or TSNE. I'm going to have to look into what that is. By reducing the 512 dimensional vector down to 203 dimensions, you can plot the features as points in 2D or 3D space, helping you see clusters or trends. Okay, feature map style visualization. Visualization of feature maps is more common with convolutional layers, but with linear layers, you can still visualize each of the 512 activations as a grayscale value in a grid. Yep, I wanted to do that. Uh, BA, hello. I love how you study. Thank you. Appreciate it. Hello. Welcome to the stream. We are learning how neural networks see things, how specifically how feed-forward neural networks uh, understand the data. I'm trying to understand exactly what the neural network is extracting from the input data, and as the data passes through the neural network and is of course transformed, what exactly is happening there? Why is it being transformed? What kinds of data is being what kinds of features are being extracted from that data? Okay, so where was I? Visualization of feature maps is more common with convolutional layers, but with linear layers, you can still visualize each of the 512 activations as a grayscale value in a grid. It's important to remember that the arrangement is arbitrary and doesn't reflect any inherited spatial structure. Okay, okay. So then what if I tried to build now I need to find a good way to visualize this because okay, maybe there's a better way to visualize. So it would probably help if I knew what exactly I'm visualizing. I would probably be able to make a better guess for what method I should use for visualization. Because so far, I'm just going with the simplistic approach, which is, oh, this is an image, we flatten this. And so, because we flattened it, let's try to rebuild another image out of the processed data or out of the result, just so we can visualize that as well. So, I'm trying to visualize that as an image, though I don't know if that's going to reveal anything useful necessarily. I'd imagine with convolutional neural networks, we might be able to get something more useful out of it because you have like two-dimensional and three-dimensional stuff going on there, but here it's kind of different. Here you have to flatten the data and then pass it into the input layer, or well, that is the input layer. You have to then pass it into each of the hidden layers. So once you've flattened the data, then I don't know how much good is going to come out of rebuilding an image out of it because the thing gets flattened like out on the other end. It's not even generating another image. What it's doing is it kind of picks apart this entire data, and in the end it spits out probabilities, which in this case, because it's a classification network, so it kind of needs to do that. But the point is we are getting probabilities at the end as a result. We are not getting another image. So the thing is kind of like just like destroying the entire structure of the data. In fact, the moment I feel like the moment we flatten the image, we've already destroyed the structure of the data. So anything that could have been visualized is now gone. I mean, the neural network is still able to pull information from it. That's kind of why we are destroying the structure of the data, just so this specific kind of neural network can pull information from it. But like once we've done that, we can't really, you know, rebuild that structure. So we need to find a way to visualize the data in whatever form it's in. Okay. Feature map style visualization. So they're saying that this is more common in convolutional layers, but with linear layers, you can still visualize each of the 512. Okay, all right. Useful libraries. PyTorch plus matplotlib slash seaborn. For basic heat map visualization, you can use matplotlib's imshow or seaborn's heat map function to plot the reshaped feature vector as a grayscale or a color heat map. Okay, we can try that. Though I wonder if we need to yeah, I wonder if we still need to like rebuild an image out of the data before we can plot the heat map, because the heat map is also two-dimensional, isn't it? If all we have is a one-dimensional vector, then we have to find a way to like make a square out of it so we can then visualize that. Okay. So, right. TensorBoard. Okay, TensorBoard is something that I haven't touched yet. Like I read up on it, but I don't think I went too deep into it. I'm also not entirely sure how much I'm going to be able to use TensorBoard if I'm doing stuff using Kaggle notebooks. Uh, I I need to read up on TensorBoard and fully understand exactly what the system is and how we are meant to be launching it before I can, figure out whether TensorBoard can be used with Kaggle notebooks. Okay, PyTorch integrates well with TensorBoard, which enables the visualization of embeddings using add embedding method. This is particularly useful if you apply PCA or TSNE to reduce dimensionality first. Okay, feature visualization libraries. Libraries such as Omni XAI offer more advanced optimization-based feature visualization tools, although these are often focused on convolutional networks and may go beyond simple linear layer outputs. There are also open source repositories on GitHub like PyTorch CNN visualizations. Is this the same as CNN Explainer? Because there was a CNN Explainer which was super useful. But okay, let me look this up. Give me a second. PyTorch, CNN visualizations. I don't know if this is a dynamic system. Like, can we customize the thing? BA7. Thank you for the follow. Hello, hello. Convolutional neural network visualizations. Let's open this up here. Okay, this repository contains a number of convolutional neural network visualization techniques implemented in PyTorch. Implemented in PyTorch. PyTorch implementation. Oh, it's implemented using PyTorch. Okay, all right. I removed CV2 dependencies and moved the repository towards PIL. A few things might be broken. I would appreciate if you create an issue if something does not work. Okay, this is interesting. Hold up, this is very interesting. So I'm going to keep this in mind for when I later get into convolutional neural networks. I'm going to open it up here so you guys can also see what I'm looking at. Um, how is this still being maintained? Yeah, the last update was to the license, which was 3 months ago. I don't know if it's still being maintained, but that doesn't mean that it's not going to be useful. I'm gonna PyTorch CNN visualization. Open it up here and we should be good. Okay. Right. So this is the repo. Um, and it seems like they've done a ton of work because there's a bunch of different methods that they've implemented, and they've also given examples of how stuff is being visualized. Or well, they've given visual examples. I don't know if it's exactly how the stuff is being visualized, but well, yeah, okay, this is how it's being visualized. So they have gradient visualization. Um, I never thought about that. I never thought about gradient visualization. Actually, I did back when I was learning the theory of feed-forward neural networks, but it was specifically gradient descent, where just being able to visualize how the data kind of converges towards, or not the data, how the loss converges towards minimum. It's kind of an interesting, like it basically looks like a valley. If you, though, okay, my understanding of that is that the visualization is apparently being done from multiple different angles. It's not just one angle, because I'm not sure how to explain it, but yeah, it's not just one angle. I don't know how to explain it, but yeah, okay. Hierarchical gradient visualization. Okay. Grad times. Okay. Smooth grad. Convolutional neural network filter visualization. Okay. All right. Uh, okay. Deep Dream is technically the same operation as layer visualization. The only difference is that you don't start with a random image, but use a real picture. The samples below were created with VGG19. The produced result is entirely up to the filter, so it's kind of hit or miss. Okay, all right. We'll look into that later. Class specific image generation. Okay, cool. So this is a library that, yeah, we might need to install this. I wonder if this is already installed, and because all of the dependencies that are listed here, they're definitely installed in Kaggle notebooks. I think even PIL might be installed already. What's the name of the what's the exact name of the package? Is it this PyTorch CNN visualizations? I think that might be, yeah, I think that might be it. Okay, all right. Let's carry on reading this. So, naive, naive reshape and heat map. Okay, yeah, I could try the reshaping thing, because to a certain extent, I think it maintains some structure in the data, even though the data is being flattened. Um, I think there's going to be, so okay, the data has been flattened, right? But it's probably going to maintain structure in terms of like being sliced, if that makes sense, because like that's kind of what's happening, right? Imagine the image has been sliced, and then all the slices are just like laid out, well, sliced horizontally, and then all the slices are just laid out one after the other. That's essentially flattening. Though, um yeah, I didn't take into account how, like the order of the pixels, the order of the features. So I can't say for sure if it's exactly like, laid out in order, but yeah, okay. Uh right, so that's our features. This is reshaped, okay. I am show. What was it? Okay, so this is a 16 by 32 image. 16 by 32. Um right, wait. Oh, okay. I didn't think of that. That's that's interesting. This brings me to another question here, which would be, um, uh, how do I say this? I have an image. I have a 28 by 28 image, which I flatten into 784 pixels. I then feed all these features into uh, into a linear 784 512 layer. After getting the result, I want to make uh, the 512 features into an image. So I reshape the vector into 16x32. I'm wondering what are good ways to go about coming up with. No, let me also mention. So I reshaped the vector into 16 by 32 since I cannot create a square image out of it because 512, no, because the square root of 512 is not a whole number. I'm wondering what are good ways to go about coming up with dimensions for an image when faced with such situations. Oh God, let's stop. This specific question, I only want uh, a simple answer to. Well, not a simple, but I for this specific question, I don't want to see the thought process. Though, to be honest, even in the future, if I do end up in this kind of a situation, I'm probably just going to come back and ask a language model that, hey, I have so and so number of features. I want to turn this into an image. What's a suitable dimension for this? And then it's going to give me a suitable dimension. Okay, when you have a feature vector of length 512, after, for example, passing an image through a linear layer, and you want to visualize or use it as an image, the dimensions, hold on. The dimensions for reshaping present, what? Hold on. The dimensions for reshaping present a common challenge. Since 512 is not a perfect square, you cannot reshape it into a square image. Approaches for reshaping non-square vectors. Closest factor pair, rectangular shape. Find two integers whose product is 512 and whose difference is minimized. For 512, some common factor pairs are so and so. This method is used widely to maintain as close to a square aspect ratio as possible. This often helps with downstream tasks in convolutional neural networks. Padding or cropping. Yeah, that works. Padding or cropping works. Oh, hold on. Speaking of padding and cropping, dude, Torch Vision had both a padding and cropping thing. So I wonder if I would be able to use one of these images to sort of, create a cropped thing. Actually, in this case, not a cropped thing, but a padded thing. TLDR, we recommend using V2 instead of those in so and so. Okay, they're faster and they can do more things. Just change the input. Okay, all right. They can transform images, but also bounding boxes, masks, or videos. This provides support for so and so. Okay, they support more transforms like cut, mix, and mix up. They're faster. What did I just do? Okay. They support arbitrary input structures and so on. So okay, all right, cool, cool. Yeah, I'm gonna read up on this more to see to what extent I'm able to use this to solve my issue. Resize the input to a given size. I would still need to convert the thing into a square before adding the padding, right? Okay, let's see. Hold on, hold on. We had something here. Uh, okay, channel-based reshaping. Okay, all right, recommended practice. So the standard approach is to reshape it into this, a rectangle as close as possible to a square. You know what? Yeah, I think I'm just going to come back and ask a language model in the future, either how to figure out a good. I mean, I'm going to ask how to figure out a good calculation for, you know, um, reshaping that 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 vector. But what's going to end up happening is it'll give me the formula, and it'll then also give me an answer or its suggestions or something, and then it's just going to be I'm just going to use that. Okay, so this is one way to go about it, where we reshape the thing, and I'm probably going to be using that. Then we have dimensionality reduction. So try reshaping your 512 features to a 2D grid, example so and so, and visualizing. Oh, wait, no, this is a summary of the entire thing. This just gave an. Oh, it mentioned PCA somewhere up here, I think. Yeah, dimensionality reduction techniques. Okay, I could read up on PCA, and well, this gives me a reason to read up on PCA, which is great because I haven't been doing nearly as much data science, or more specifically scikit-learn studies, as I would like to. But the good news is that I've been making progress, at least with deep learning, so I'm not complaining. Okay, cool. Now, um, we were here, right? Where exactly was I? I should explain how the network transforms data in each layer. Okay, also address how the user might. Okay, yeah, no, back. So I finished this part, overfitting, which, by the way, I don't think I ever produced that. Yes, I need to note that down as well. Uh, Produce examples of overfitting and underfitting, which, I mean, underfitting is basically just the network does a shit job of classifying data. At least that's my understanding. It does a bad job of classifying the data. Overfitting is when it does a great job on specifically its training data, but then when you give it something that's outside of the training data, then it's gonna have issues. So it doesn't generalize very well. That's what I need to reproduce. And I have no idea how I'm gonna do this specific thing, but I'm gonna write it down anyways. Also, find a way. I think I did write this down in like a big list previously. The list is somewhere here. It was in this notebook. Oh yeah, this is one of the images. I was mentioning at the beginning of the stream that um, I started using the MNIST dataset as well, because like in the example we were taught to use the fashion MNIST dataset, but then to use the MNIST dataset, all I had to do was literally just switch out which dataset was being plugged in, and everything else was the same. It was the same neural network structure. It was the same training loop, the same test loop. Everything was same, and nice coincidence. Even the images are the same size. They're 28 by 28 images. I think this might have been it. Yeah, I wrote a bunch of things down here. Uh, yeah, I'd also mentioned this thing. Understand how changing the number of hidden layers affects the neural network. Where did I mention? I do remember writing down both overfitting and underfitting. Where did I write that down? That's okay. Even if like okay, I can also find a way to visualize overfitting. I have no idea like what this entails and what exactly we are visualizing here, but like we'll at some point I want to try and do that. Okay. ReLU activation introduces nonlinearity, allowing the network to model complex patterns without it, even multiple layers would just be a linear transformation. Softmax at the end converts the outputs to probabilities. I should explain how the network transforms data through each layer, maybe use an analogy like feature hierarchies. Lower layers detect edges, mid layers detect shapes, higher layers combine them into recognizable objects. Okay. Also address how changing the number of layers and neurons affects model capacity. Too few and the model can't learn complex patterns. Too many and it might overfit. Maybe mention the trade-off between underfitting and overfitting. The user might not grasp how training via backpropagation works, but since they mentioned they know how to train, maybe focus more on the forward pass and what each layer represents. Thank you. Yes, I definitely appreciate that. Because, okay, I do feel like there's something to be explored in I do feel like there's something to be explored in how do I say this? So initially all the weights and biases are untrained, right? They're random values, or random to a certain extent. They're random values, which we then, with each training iteration, we change them to minimize the loss. I just lost my train of thought. What was I trying to? I was about to say something about visualizing something during backpropagation. I forgot exactly what I was trying to visualize there, but okay, let's focus on visualizing this. Okay, perhaps use a concrete example. Imagine a simple feed-forward neural network for MNIST with two hidden layers. The first layer might learn to detect edges in different orientations. The second layer combines edges into parts of digits, and the output layer combines parts into whole digits. Also, touch on the role of the loss function and how the network adjusts weights to minimize loss. Also touch on the role of the loss function and how the network adjusts weights to minimize loss. Okay, yeah, that's part of the training. Each neuron's weights are adjusted to contribute to correct classifications. Okay, I should make sure to clarify that each layer's neurons are like feature detectors, and the network as a whole is a complex function approximator. The depth and width allow the model to allow the model what allow it to model more complex functions. Finally, check if there's anything I'm missing. The user mentioned not understanding what patterns each layer captures. Maybe visualization techniques could help. But since they're asking for an explanation, focus on conceptual understanding rather than tools. Okay, let's break down how feed-forward neural networks work, what hidden layers and neurons do, and how they capture patterns in data. How they capture patterns in data like MNIST and fashion MNIST. Your confusion is common, so we'll start with intuitive analogies and build up to technical details. What does an FCNN do? An FCNN transforms input data, example pixel values, into predictions, example class probabilities, okay, through successive nonlinear transformations. Each layer represents the data in a way that makes it easier to separate into classes. Think of it as a series of feature extractors. Run that back. Each layer re-represents the data. Each layer re-represents the data in a way that makes it easier to separate it into classes. Okay? Think of it as a series of feature extractors. So the input layer is the raw pixels. The hidden layers extract increasingly abstract patterns, edges, textures, shapes, object parts. Okay, so I wonder if there is a way to visualize what they are extracting. Or is it that they are extracting it in the form of numbers? Or, well, how do I say this? Is it that what they are extracting is more of a pattern than the actual things themselves? So I wonder if it's extracting a pattern that represents the edges rather than the edges themselves, meaning trying to visualize that is not really going to show the edges, if you get what I'm saying. So I wonder if it's the same thing with edges and textures and shapes and object parts. So like I wonder if the network is extracting this information in a way that the network can understand and future layers can understand, but not necessarily in a way that could be intuitive to visualize, if that makes sense. Anyways, output layer combines high-level functions to produce class probabilities. Okay, cool. Role of hidden layers and neurons. Hidden layers, depth, which is the number of layers, determines the complexity of features the network can learn. Shallow networks, 1 to 2 layers, capture simple patterns, example edges, blobs, etc. Deeper networks capture hierarchical features, example shirts in fashion MNIST equals sleeves plus collar plus texture. Dude, you know what I'm wondering? I'm wondering if all of this stuff is kind of like spread out all over the place. In the sense, I wonder if like the fact that it's able to detect edges here and textures there and color here and whatever, I wonder if like all of those features are like spread out across the network in different ways. I mean, it's based on what it's saying here, it's probably each layer that is doing that, but I wonder if there's a chance that it's spread across the entire network, and depending on the weight values, the initial weight values that you get, could it be that each time you're gonna end up you're gonna end up with a different structure of feature extractors? I have no idea if that makes sense, but like it makes sense to me. I have no idea if it makes sense the way that I've explained it, but like, so we know that there are feature extractors in the neural network, right? The hidden layers, they have feature extractors, or they are feature extractors. What I'm wondering is there a chance that depending on what the initial weights are and how the neural network goes about learning, could it be that the feature extractors will be spread out in different locations, and each time you train the neural network newly? Well, I mean, that doesn't make sense, does it? Because like each training epoch would then change where the feature extractors are. My point with this was that I wonder if the feature extractors don't always look the same in the neural network. Yeah, that's what I was trying to get at. That I wonder if the feature extractors are each time we have like a different layer or a different set of different group of neurons that are responsible for extracting certain features, but like different parts of the network end up having these different feature extractors and they kind of like change. I don't know how to find that out though. Dude, there's a lot to explore here. I need to stick with this. There's a lot to explore here. Okay, width. Neurons per layer controls how many features the layer can detect. More neurons equals more parallel detectors for patterns. Example, 64 neurons might detect 64 different edge orientations. ReLU activation introduces nonlinearity, so the network can model complex relationships. Without ReLU, the network collapses into a linear model. ReLU also acts as a filter that only allows strong signals to pass. Yeah, ReLU doesn't allow negatives, right? If a neuron detects an edge, ReLU lets it activate. Otherwise, it outputs zero. I need to explore what that means. I need to well understand what that means. If a neuron detects an edge, it lets it activate. Oh, it lets it activate as in it just passes the value through. So let ReLU will just let it through. Otherwise, ReLU will set it to zero. Okay, softmax converts to final. Oh, good. Okay, it's continuing. For a second I was concerned. I was like, is that it? Is it gonna stop at softmax and then I'm just not getting proper information? But no, it's going more into detail. Okay, it is going into more detail, but the thing is, unfortunately, I need to end the stream, and this is completely on me. I should have started earlier, but I got kind of busy with something. So here's what we're gonna do. Okay, I'm gonna go raid Oz, and we're gonna hang out in Oz's stream for a bit. Oz is cool people. Oz is a friend. Oz is also a game developer and a gamer. Today she's doing game development. BA7, thank you for stopping by. Thanks for chatting, and also thank you for the follow. Anyone else who might have been lurking in the chat, thanks for hanging out. I appreciate you guys being here. We made some good progress here. I'm gonna carry on reading up on this. There's tons for me to explore, like alone in feed forward neural networks alone. There's tons of stuff for me to explore, and I'm gonna continue learning. Hopefully I might be done reading this before the next stream, but I don't know. Let's see if that happens. But yeah, dude. I'll try to stream again tomorrow. Hopefully I'm able to. That being said, I hope you guys have a nice day, and I'll see you all next time. Peace.